Let's begin by looking at the Kenyan coast as a single system, stretching from Lamu in the north, down through Malindi, Kilifi, Mombasa, and toward the Tanzanian border near Diani. This coastline hosts the country's rapidly growing settlements and its busiest port. Notice how demand clusters. Mombasa dominates as an urban and industrial hub, while tourism and agriculture pull water along the corridor between towns. The recognizable features here matter: roads, river mouths, and dense built-up areas, because any desalination concept must connect the sea to these people. Keep in mind, this is a planning-level overview, not survey-grade mapping. We're identifying where water is needed and where a coastal plant could plausibly sit. As we move forward, remember that every demand center implies pipelines, storage tanks, and community impacts we will have to justify carefully. Now let's confront the number itself. 5 million cubic meters a day is enormous, roughly 2,000 Olympic swimming pools every single day. To produce that with reverse osmosis, you'd need on the order of 15 to 20 gigawatt hours daily, comparable to a large power station running purely for water. The plant footprint, intakes, membrane hulls, brine outfalls, and treated water tank farms could span hundreds of hectares near the shore. For water security, this volume could serve many millions of coastal residents, but it also concentrates enormous risk in one facility. These figures are illustrative, not engineering estimates. Real values depend on salinity, membrane efficiency, and energy source. The point is scale awareness. Before drawing a single pipeline, we must respect that this is one of the largest water projects imaginable, demanding careful energy, land, and environmental justification. To size and site anything, we need to see where people and water stress actually concentrate. Picture population density layered over the coast. Bright hotspots at Mombasa and its mainland suburbs, moderate clusters around Kilifi, Malindi, and Diani, and sparser rural stretches between them. Overlay water stress, seasonal shortages, saline boreholes, and unreliable pipe supply, and the pattern sharpens. Demand isn't evenly spread. It follows cities, tourism strips, and industry. This matters because a 5 million cubic meter plant shouldn't push water uniformly. It should feed elevated balancing reservoirs and booster stations near these demand nodes. Remember, this data layer is conceptual, drawn from public census and modeled estimates, not verified household surveys. Field validation, community consultation, and equity questions come later. For now, we're establishing why the coast and which parts of it could ever justify a project at this scale. Let's begin our search along Kenya's coastline, scanning 4 candidate locations for a 5 million cubic meter per day desalination plant. Moving north from the Tanzanian border, we first see Vanga, a quiet estuarine town near lush mangroves. Next is Mombasa, our busiest port, dense with roads, rail, and existing water demand. Further north lies Kilifi, with its calmer creek and growing settlements. Finally, Lamu, remote and historic, near a new deep water port. Each dot on this satellite view represents an opportunity and a challenge. Notice how vegetation, reefs, and built-up areas differ dramatically between them. Remember, these are conceptual planning markers, not survey-grade coordinates. A real field team would refine every footprint by walking the ground and confirming access. Now switch from surface imagery to terrain, because a plant this size needs large buildable land close to the shoreline. Study the elevation here. Mombasa offers flat coral platform, but almost every parcel is already occupied, so free land is scarce and expensive. Kilifi shows rising ground above the creek, giving room for intake structures and adjacent treated water tank farms on higher ground. Vanga is low and marshy, raising drainage and foundation concerns. Lamu has open flatland near the new port, but soft soils may demand deeper engineering. We also want elevated positions inland for balancing reservoirs feeding gravity distribution. These terrain readings are conceptual. Geotechnical drilling and cadastral checks on land ownership must confirm what looks promising from above. Before we get attached to any site, we must overlay the environmental exclusion zones shown here in red and amber. Kenya's coast is rich with protected treasures. Mombasa Marine Park, the Kisite and Watamu reefs, and extensive mangrove forests near Vanga and Lamu are all sensitive. Seawater intakes and brine discharge can harm reefs, seagrass, and fish nurseries, so these must stay well clear. Mangroves also guard the shore against erosion and store carbon, making them poor sites to clear. Lamu Old Town's World Heritage status adds further caution. Every red zone narrows our options and protects communities who depend on fishing. This risk map is a screening tool, not legal approval. Formal environmental impact assessment and community consultation remain essential before any commitment. Let's bring everything together in a simple scoring matrix. We rate each site across land availability, terrain suitability, environmental risk, proximity to demand, and community benefit. Mombasa scores high on demand but low on free land and reef sensitivity. Vanga struggles with muddy coastal ground and dense mangroves. Lamu offers space but sits far from the biggest water needs and faces heritage constraints. Kilifi emerges as the balanced choice. Workable terrain, room for tank farms and booster stations, reasonable distance from protected reefs, and strong regional benefit. So our preferred concept centers on Kilifi, feeding coastal demand nodes. Treat this ranking as a reasoned starting hypothesis. Field validation, geotechnical surveys, and honest community engagement must confirm or overturn it before real engineering begins. Let's begin by looking closely at the chosen coastal parcel from above. Notice the shoreline curve, the fringing vegetation, and the existing dirt track that connects the site to the nearest tarmac road. This surface view helps us judge construction access, lay down areas for pipes and pumps, and how far heavy trucks must travel from the highway. We can see nearby settlements and small fishing landings, which matter for community consultation and shared shoreline use. Remember, this is a conceptual planning view built from satellite imagery, not a surveyed boundary. Land ownership, easements, and protected mangrove edges must be confirmed on the ground. What we want here is a first honest picture of where the plant footprint could plausibly sit relative to people, roads, and the sea. Now shift attention to what lies underwater just offshore. This slope heat map shades the seabed by steepness, warmer colors marking sharper drop-offs. For a 5 million cubic meter per day intake, we want water deep enough for a reliable sediment pore supply, but not so far that pipeline costs explode. The brine outfall is a different problem. We prefer a zone where currents and moderate slope help dilute and disperse dense, salty discharge away from sensitive habitat. See how the gentle nearshore shelf gives way to a steeper gradient further out. That transition is a candidate corridor. Treat these gradients as conceptual, derived from coarse bathymetry. Real placement demands multi-beam surveys, current measurements, and dispersion modeling before any engineer signs off on intake depth or outfall diffuser location. Geology decides what we can actually build and bury. This overlay distinguishes coastal coral limestone, sandy sediments, and firmer bedrock zones beneath the site and nearshore floor. Reef limestone can support foundations but complicates trenching and may host protected coral. Soft sediments are easier to dredge for pipelines yet demand scour protection and careful settling analysis. For the plan itself, we want stable ground that resists erosion and undercutting during storms. Notice where firmer material appears close to shore, offering better anchoring for intake and outfall structures. This is interpreted geology, blending regional maps with imagery, not a geotechnical report. Boreholes, seismic profiling, and diver inspections must confirm rock quality, sediment depth, and habitat before pipelines are routed or foundations poured. Getting this wrong risks cracked pipes, sinking structures, and lasting ecological harm. Finally, let's assemble a prototype plant layout on the parcel. Seawater enters through the intake, passes screening and pretreatment, then feeds banks of reverse osmosis trains that produce fresh water at enormous scale. Treated product water flows to an adjacent tank farm, then to an elevated balancing reservoir and booster station feeding coastal demand centers nearby. Concentrated brine returns seaward to a diffuser outfall, kept well clear of the intake to avoid recirculation. Power supply, chemical storage, and access roads frame the site. This block plan is conceptual, showing spatial logic and separation distances, not final engineering. Detailed design must address energy sourcing, brine dilution limits, community water benefit, safety buffers, and environmental permitting. The goal here is a defensible starting arrangement that a survey and design team can test, refine, and validate in the field. Let's trace the water uphill. Here, the horizontal axis follows the corridor from the coastal plant, while the vertical axis shows elevation gain toward an inland balancing reservoir. Notice how the plant sits near sea level, then the profile climbs gently across the coastal terrace before rising to a ridge where an elevated reservoir could store treated water and provide gravity pressure to demand nodes below. Every meter of lift costs pumping energy, so we want the reservoir high enough to serve customers by gravity, but not so high that lifting 5 million cubic meters daily becomes ruinous. Remember, this profile is conceptual planning geometry sampled from public elevation data, not a surveyed pipeline centerline ready for engineering approval. Now, overlay the product water route on the surface. It begins at a plant-adjacent tank farm where treated water is buffered before entering the transmission main. From there, the line follows road corridors inland, easing land access and maintenance, passing 1 or 2 booster stations that lift water toward the elevated reservoir. Branches then feed coastal towns and demand centers along the way. Keeping the route beside existing roads reduces new land take, limits erosion from fresh cuts, and respects settlements and protected zones we must avoid. This is a coastal regional distribution concept, not a national transfer. Treat these control points as inspection candidates a survey team would walk, verify against land ownership, and refine before anything is fixed. Zooming to real surface detail, we search for reservoir and booster sites near where people actually live. A good elevated reservoir sits on stable high ground close to demand, with road access for construction and a footprint clear of housing, farmland, and sensitive habitat. Booster stations want reliable power, drainage away from the tanks, and enough setback from communities for safety. On this satellite view, we can read land cover, existing tracks, and settlement edges that hint at ownership and likely objections. Siting here is about community benefit and fairness, not just hydraulics. Everything you see is a candidate for field validation, geotechnical testing, and consultation, not a confirmed parcel or an approved engineering decision. Finally, let's fly the whole corridor in 3 dimensions. We lift off over the seawater intake, sweep across the plant and its tank farm, then follow the transmission main inland as the train rises beneath us. Watch the booster stations mark each climb and see the elevated reservoir crown the ridge before gravity carries water back down to coastal demand nodes. This flyover helps you feel the elevation story that flat maps flatten out, where energy is spent lifting and where slope does the work for free. Keep in mind this is a raised terrain conceptual journey built from public data. It illustrates the planning logic, but it is not a survey-grade alignment or an engineering commitment. Every large desalination plant produces concentrated brine, and along this Kenyan coast that discharge meets warm, biodiverse water. Watch the risk zones shaded here. Near the outfall, salinity and sometimes temperature rise, stressing seagrass beds, corals, and nursery fisheries that communities depend on. Diffuser design and offshore placement can spread the plume, but nothing eliminates it. Notice also the erosion-prone stretches where intake and outfall structures can alter longshore sediment transport. These bands are conceptual planning overlays, not surveyed impact contours. Before approval, we would need current meter data, seasonal monsoon modeling, and baseline ecological surveys. The honest takeaway, brine and erosion risk are manageable only if we study them early, cite the outfall carefully, and monitor the reef continuously afterward. 5 million cubic meters a day is enormous, and this infographic lays out the trade-offs. Reverse osmosis at that scale demands gigawatt-level power, so the plant lives or dies on its energy source. Solar and wind reduce emissions but need land and storage. Grid power may be cheaper, but its carbon intensity depends on the supply mix. Land ownership matters too. Much of this coast is customary or community held, so a project cannot simply claim a footprint. Fair compensation, transparent consultation, and local water access are ethical minimums, not afterthoughts. Community benefit should be concrete, piped water to nearby towns, jobs, and shared elevated storage tanks. Every mitigation choice trades cost against harm. These figures are illustrative planning ranges, not audited engineering budgets or negotiated agreements. A coastal plant does not just interact with the sea, it sits inside a watershed. This drainage map traces the small seasonal streams and stormwater channels that cross the site toward the shoreline. During heavy monsoon rain, runoff concentrates here, and if plant discharge or chemical handling areas lie in these flow paths, contamination can spread downstream or pool near settlements. We want the treated water tank farm and any chemical storage sited on higher, well-drained ground away from these blue channels. Stormwater should be separated from process discharge, not casually mixed. These flow lines are modeled from elevation data, so treat them as conceptual guidance. A real design needs surveyed drainage, culvert capacity checks, and flood return period studies before anyone pours concrete. So how do we move from these concept maps to something a regulator could approve? This animation walks through the control points the survey team would physically inspect. First, the intake site, check seabed depth, currents, and marine life. Second, the outfall and diffuser location, confirming the brine plume disperses away from reefs. Third, the tank farm platform, verifying stable, well-drained ground. Fourth, the distribution corridor toward demand centers, checking land ownership and access. Fifth, drainage crossings for flood risk. At each point, teams collect coordinates, soil or sediment samples, ecological baselines, and community input. The animation shows how each validated point tightens our confidence. Remember, this is a planning framework, not approval. Only field-verified data and formal environmental assessment can confirm feasibility. This KML exports the selected Kilifi concept for Google Earth, including the intake, plant, treated water route, and separate brine outfall side branch. This GeoGSON records the selected Kilifi intake, plant storage, reservoir demand connection, and separate brine outfall control point. This MapLib reviewer centers the selected Kilifi concept and separates the product water route from the offshore brine outfall branch. So, can a 5 million cubic meter per day plant be done at the Kenyan coast? Physically, the concept is not absurd, but at this scale it is enormous, and our verdict stays honest, conditionally plausible, deeply uncertain, and far from approved. What we've built here are conceptual deliverables, not engineering sign-off. The real next steps are serious: bathymetric and geotechnical surveys, brine dispersion modeling, energy sourcing, protected area and reef screening, land tenure checks, drainage and erosion studies, and genuine community benefit agreements. Take these KML, GeoGSON, and viewer files as a shared starting point. Let them provoke better questions, then hand them to specialists who can turn cautious concepts into responsible survey-grade decisions. Please see the references for further reading.